access memory, but it's really expensive and it's not very high capacity, so it's not in most computers today. There's other kind of neat ideas for using magnets to store information too. If you take a long nanowire, you can actually push domain walls, that's these red and blue sections here, through the wire just by putting a current through that wire. And the way they move around is a subject of a lot of research at this point in time. But it's clear that they can be pushed through that wire. And this idea right here, where you have the wire going down and then back up again, and it goes past a little sensor at the bottom, is called racetrack memory. And it was actually written up in Scientific American just last summer. And the idea here is that if we want to make memories denser and denser, at some point we can't make them any smaller because we start to run out of atoms to write information on. So why not try and stack up the bits vertically? And then the other thing is that that makes it a little bit challenging to read with a read-write head. So let's try and push the bits around instead of moving the head around. So it's kind of a neat idea, and it's in the research stage at IBM right now. And there's a lot of people who are doing work looking at what happens when you try and push domain walls around inside nanowires. And it's kind of an interesting subject. So in addition to storage media, magnetic nanoparticles also have applications in biomedicine. They're used for things like, or the idea is to use them for things like targeted drug delivery as a means for detection and manipulation. So if you have magnetic nanoparticles that you can move them around with magnetic fields, and that can be useful in certain conditions. And we can functionalize them with all sorts of biological stuff. And we can use them for image contrast. And if you put an AC field on, if you turn on a magnetic field that changes as a function of time, then you can actually cause those nanoparticles to heat up. And this is a really promising idea for treating cancer in particular, because you can attach, the idea is you can attach the nanoparticles to cells that are cancerous, and then you cause them to heat up, and that will destroy the cancer cells preferentially. And obviously it doesn't involve a lot of heavy-duty chemicals in the body, so that's kind of a nice alternative. Yeah.
And how did you say you would heat them up?
Well, magnetic materials undergo a process called hysteresis. Hysteresis means that the magnetic moment of a system depends on the history, the magnetic field history in this case, of the sample. And hysteresis is associated with energy loss. And energy loss usually or often generates heat. So all you have to do is change the magnetic field from one direction to the other. That moves the magnetic moment back and forth, and in the process you cause it to heat up. Now the details of exactly how one might do that to use for something useful for an application like this are much more complicated, but that's the general idea behind it. There's another way that you can actually use magnetic materials for medical applications. If you take, and this is a really recent example, if you take little tiny discs, and this is an optical microscope image, so each one of these is about 1 micrometer, so 1,000th of a meter in diameter. These little tiny discs, all the spins will curl around in a circle like this into a vortex. And a vortex, we have all the same number of spins pointing in this direction as we do this direction, as we do this direction, and this direction. So it's like a totally magnetized piece of material, except all of the directions cancel out. And so it doesn't have any stray magnetic fields associated with it. Well, for biological applications, that's very important because magnets stick together. If you put two magnets close together, they're either going to stick together or repel. And if you let them do whatever they want, they'll rotate so that they'll stick together. And things sticking together inside the body would be bad because that would cause all sorts of problems. So having zero magnetic moment is really a useful thing. Now, if you watch this little movie here, what you'll see is that it gets bright and dark as a function of time. So what's happening here is we're turning on and off a magnetic field. And when you turn on and off the magnetic field, these little tiny vortices, they're randomly oriented most of the time, but when you turn on the magnetic field, they all align along the direction of the magnetic field, and then the light can go straight through. And so what this little movie here is showing is that you can actually rotate these little disks with a fast-moving magnetic field. Now, the reason you might want to do that is because, well, if you take these little micron-sized disks, they're about the same size as a cell, and you can actually functionalize these disks. You can put on some kind of a molecule that attaches onto the outside of the cells here, so that your disks are attached to the cell, and then if you rotate them back and forth, they will damage that cell membrane wall, and that will lead to cell death. And it's been demonstrated that this will actually work if you put the little functionalized biodiscs in with a bunch of cells. Then you can rotate them around and have a pretty good success rate at killing the targeted cells. So this research is still a ways away from being anything that's used in real therapies, but it shows kind of a different way of using nanomagnets for biomedical applications. So I've talked a little bit about some of the reasons why nanomagnets are interesting and why they're useful and where you might see them in everyday life. Now I want to tell you a little bit about how we actually go about building them. And there's a few different ways to do this. And the other speaker will talk a little bit more about the bottom-up techniques. This is where you put all the materials in. It's like cooking. You put in all the ingredients into a beaker usually and treat them in some way, and all of the materials agglomerate into nanomaterials. So you're building them from the bottom up. We can also do it from the top down, and this is the direction that my research usually uses. So in this case, we're starting with a bigger magnetic material, usually a thin film that we've laid down, and we cut it into smaller pieces. And we cut it into smaller pieces using something called lithography. So we actually use polymers, which are the same type of material as what you find on the shields on hockey rinks, for example, or other sporting events. And we spread that in a thin layer on top of a substrate, and then we expose it. We shine either electrons, here the green one works better, electrons, or we shine light through a mask onto certain areas of that structure, and then we dissolve the areas that have been exposed. And then when we put down a metal later on, we can take away the metal everywhere that's sitting on top of the polymer, and we're left only with the metal that's sitting in between in the holes. And this lets us write structures down to tens of nanometers in dimensions on top of flat surfaces. And this is done, so I told you before that human hairs are about 200 micrometers. There's a lot of other dust and dirt that's floating around in the air. And these are all huge compared to the size of the samples that we're working with. So a lot of the fabrication is done in what we call clean rooms, where you try to eliminate a lot of the dirt and the dust. And a lot of the dirt and dust that you're trying to eliminate actually comes from you, from your skin, from your hair. So we wear what you call bunny suits, because all you need to add are the little ears and the tail for wearing it out for Halloween, into the clean room. And we load up the samples into fancy pieces of equipment that are used to then, we focus in on the samples and we write the patterns using beams of electrons. As I said, the other way to do it is to assemble the nanoparticles using chemistry from the bottom up. And the next speaker will talk more about how that's done, I think. You also find magnets that are nano-size in dimensions in biology. Little tiny bacteria called magnetotactic bacteria actually have little chains of magnetic nanoparticles that they make themselves. And this is a picture that somebody else took using an electron microscope. So each of these little dots right here, these are a chain of magnetic nanoparticles that have their moments all lined up in the same direction. And it's thought that the magnetotactic bacteria use this as a little compass. So they use the Earth's magnetic field and their internal nanoparticle compass to find their way around. And you can also use biology as a template. So it's been shown that you can take a virus and empty out all the DNA and replace it with something magnetic and use that to make nanoparticles with a very uniform size distribution. We also look with computers. I'm not going to talk very much about this, but you can use computers to calculate what happens in magnetic materials in very small structures. And in this example, what we have is a little magnetic vortex that's forming here in a cylindrical structure. So this is a flat pancake type structure. in which we find vortices quite often.